In chapter 4.2, we will continue with probabilities, and now we're going to look at some particular rules. The first rule, it is called the multiplication rule. Some things that you need to know is more than one event is occurring. So two or more events are occurring. This is sometimes you can think of it as the and statement or the and rule. So when you see a probability with and, you know you're going to apply the multiplication rule. Here is the formula that you're going to be using. And this reads, the probability of event A and B is equal to the probability of event A times the probability of event B given or assuming that A did occur. Now, this second part is what we call a conditional probability. This is events that occur on a condition that some event has happened first before the second event will occur. These events are dependent. So what this is saying when we say given A, we're saying B will occur assuming or given that A did occur. Okay, so sometimes a secondary way in which you will see it written is P of event A slash B. This means the same thing as the probability of A given that B occurs. So this means that event A will happen given event B has already happened. Then we have the probability of B slash A, and it's the same thing just in reverse, the probability of event B given A. So this means that event B will happen given that A has already happened. So let's apply this multiplication rule. So in this first example, it says we're going to roll the die 3 times, and it wants to know the probability that when you roll, you get a 3 on the first roll, and a 6 on the second, and a 2 on the third. So one of the things that you need to notice is and. So that tells me I'm going to apply the multiplication rule. Now this is what this would look like if you rewrote it using the multiplication rule. It would be written as the probability of 3 times the probability of rolling a 6 given that you got a 3 on the first roll times the probability of rolling a 2 given that you got a 3 and a 6 in that order on the first 2 rolls. So think about when you pick up a die. So when you pick up a die, it's a 6-side, 1, 2, 3, 4, 5, and 6. So there's 6 possible sides. When you roll that die, what is the probability that you roll a 3? Well, there's 1 favorable side to 6 sides. Now pick up the die for the second time, and now the probability that you get a 6, assuming that we already got the 3. So we're assuming this happened, so in essence we're saying this has happened, now what is the probability you get a 6? Well, again, there is 1 side that has a 6 on it, 6 sides, times, now I want to know, assume that you got the 3, assume you got the 6, so now what's the probability on the third roll that you get a 2? And that would be 1/6 as well. So you'd multiply the top and you would get 1. 6 times 6 times 6 is 216. So if you were in Vegas and you were betting money, the probability that you would get in 3 rolls that it would be a 3, then a 6, then a 2 is 1 over 216. So not great odds. That's 0.0046 and so on. So not great odds of winning money there. All right, then we have a second example. Draw 2 cards from a deck of 52. Draw the first card. Replace it before drawing the second card. And then I look at this and it wants to know what is the probability of getting king and 3. So that would be written the probability of a king times the probability of a 3 given king. So if I was holding a deck of cards and I ask you to draw, so on the first draw, what's the probability you get a king? Well, there's 4 kings, 52 cards, times, now it's saying whatever you drew, and we're going to assume you drew a king, because that's what we do when we're dealing with probabilities. This given king, we're assuming that you drew a king, okay? So you put that card back, and now what is the probability you get a 3? Well, there's 4 3s in the deck and 52 cards. So now what we're going to do is multiply and reduce this fraction. Now, I don't know, let me see, if you know, your calculator will actually do this for you. You can do the reducing of the fractions yourself, but on calculators, and this is the TI-30XS multi-view, which I highly recommend this calculator, there is this button right here, N over D, so I can put in 4 fraction button, 52, right arrow over, times, and now I'm going to put in 4 fraction 52, right arrow over, and hit enter, and it's going to give me my reduced fraction, 1 over 169. All right, now this says draw the first card, but now it says do not replace the first card before drawing the second. So we have the probability of a king times the probability of a 3 given king. So we already know that this is 4 out of 52. Now you're going to hang on to that card. So assume that you are holding a king in your hand. On the second draw, what's the probability of getting a 3? Well, there are 4 3s in the deck of cards, but there are only 51 cards left. So I'm going to go to my calculator and do 4 fraction 52 times 4 fraction 51 equals, and it reduces to 4 over 663. Now, I noticed something at the top of my notes that is incorrect. Sometimes these two events can be independent, so I'm going to mark this out right here. So that's a little deceiving. I need to tweak my notes on that, so I apologize for that. Okay. And here we're going to talk about independent and dependent events. Okay, so the first thing that we need to discuss in some terminology is independent events, and if you'll notice down here, we're going to talk about dependent. So let's look at the difference between the two. Independent events tell us that the occurrence of one event does not change the probability that the other will occur, meaning it doesn't alter the likelihood of the second event. Rolling the die. When we rolled the die 3 times, the die still has 6 sides to it, so nothing changed when I picked it up the second time and the third time. Drawing cards with replacement. As long as you replace that card, then the events that occur after are not going to be altered because all 52 cards are going to be there still. Another example, this reads, what is the probability that you roll a 4 on a die and flip a tail on a coin? So again, this and tells me that I'm going to use the multiplication rule. So what this would look like is, what is the probability of getting a 4 and tails? Now, when we look at this, this would be the probability of a 4 times the probability of tails given we got a 4. but these are independent. So on the picking up the die, there's one side that is a 4, 6 sides. Now you're disregarding the die and you're picking up the coin. So they're independent because that die is not going to alter whether you get heads or tails. Whoops, this should be the probability. Sorry about that. So when you pick up a coin, what's the probability of getting tails? We're assuming we got the 4, but it still doesn't change the probability of getting tails. It would be 1 over 2, so we have 1 out of 12. Now, one thing that you can always remember as well is this is favorable outcomes, this is possible. So the denominator tells me if I were to create a sample space, how many items would be in the sample space. Now 12 is doable. One of these examples over here, this was ridiculous. Well, let's go up here. I'm not going to have you give me a sample space that has 216 items in it, but 12 is doable. Here's what that would look like. You could get a 1 on the die and heads, 2 on the die and heads, 3 heads, 4 heads, 5 heads, 6 heads, or 1 tails, 2 tails, 3 tails, 4 tails, 5 tails, 6 tails. And there's your 12 possible outcomes, and this was 4 and tails, and there is 1 of them out of 12. And if we found the probability of each one of these, it would be 1/12, which tells me these events are equally likely. Now, how does that look with dependent? Dependent is the occurrence of one event does affect the probability of the second event. That would be drawing cards or any type of a drawing without replacement. So let's take a look at how that would look. So here we have a bag. So I'm going to draw my bag. And we have 5 red marbles. 1, 2, 3, 4, 5. 3 green and 2 blue. So we're going to draw 2 without replacement. So this is important right here. This is what tells me that these events will be dependent, is without replacement. So find the probability of drawing a red and then a green. So the probability of drawing a red and green marble. Well, first I need to know the total number of marbles in the bag. So 5, 6, 7, 8, 9, 10. So we have 10 marbles. All right, so this would be the probability of red times the probability of green, given or assuming we got a red on the first one. So when I come to this bag for the first draw, the probability that I get a red one is, all 5 red ones are in here, so it's 5 over 10 marbles. Since it's without replacement, assume you're holding a red marble in your hand. So now what is the probability of getting a green? Well, all 3 green ones are still in there, but there are only 9 marbles now. So we have 5/10 times 3/9. So you multiply that and reduce, and you get 1/6. Now, what if I changed this and I said, what is the probability of drawing a blue marble on the first draw and a blue marble on the second? So in the formula, it would be the probability of blue times the probability of blue given blue. And again, I'm still doing without replacement. So when I reach into this bag, the probability I get a blue one is 2 out of 10. But now I want you to assume that you're holding a blue marble in your hand. So now in the second draw, what's the probability of getting blue? Well, you're holding one blue one in your hand already, so there's only one other left. So this one would be 1, and there were only 9 marbles in the bag. So 2/10 times 1/9 is 1/45. So that's the multiplication rule. So now we're going to continue on and learn an additional rule. Pull that down. Now we're going to look at what is called the additional rule. Now, just like the multiplication rule is also known as the AND statement, this is the OR statement. And this is used when considering the possibility of one event or another occurring. So there's only one event or one item that's going on. You just want to know which one's going to occur. Where in the multiplication rule, more than one event was occurring. So here's the formula we're going to use when we have OR. And this reads, the probability of event A or B occurring is equal to the probability of event A plus the probability of event B minus the probability of event A and B. This would be if both of events can occur. So we'll talk about that as we work these. Okay, so this first example, we're going to roll the die one time. So just one event is occurring, but I want to know which one of these might happen. So this is OR. So in the formula, it would be read the probability of 3 plus the probability of 6 minus the probability of a 3 and 6. So when I'm calculating this, I said, okay, pick up the die one time. What is the probability that when I pick up that die, I get a 3? Well, 1/6. All right, I'm only rolling the die one time. What's the probability if I roll the die one time, I get a 6? Well, 1/6. Minus, okay, I'm only rolling the die one time. So when you pick up the die and you roll it, what's the probability in that one roll or that single roll that you get a 3 and a 6 at the same time? Well, a die cannot land on two sides at the same time. So this would be 0 out of 6 or 0. It cannot occur. So my answer is 2/6, and we always reduce our fraction 1/3. All right, next example. Draw one card from a deck, and we know there's 52 cards in a deck. This wants to know what is the probability that when you draw one card, you get a king or a 3. Well, this would be the probability of a king, and we see the word OR, so plus the probability of 3 minus the probability of king and 3. All right, so I draw one card. What's the probability I get a king? Well, there's 52 cards. I draw one card. What's the probability that card would have been a 3? Well, 4 out of 52. I draw one card. What's the probability when you draw one card that you get a king and a 3 at the same time? Well, that cannot happen, so that would be 0. So this would be 8/52, which reduces to 2/13. Now at this point you might be thinking, okay, that's always 0, so why is that even in the formula? Well, it's not always 0. Let's take a look at this example. This would be read the probability of a king plus the probability of a heart minus the probability of king and heart. Okay, so let's think through this. When you draw one card, what's the probability you get a king? 4 out of 52. When you draw one card, what's the probability that that card will have a heart on it? Well, there are 13 cards out of the 52 that have a heart on it. But then we have to subtract any cards that has a king and a heart on it. So when you draw one card from a deck, is it possible to get one card that has a king and a heart on it at the same time? And yes, there is one card out of the 52 that has the king and the heart on it. Now the reason we have to subtract one of these is because the card that is a king of hearts, it is included in this 4 and it is included in this 13. You can't add the king of hearts twice. So we have to subtract one of those. So that would give me 16 over 52, which reduces to 4 over 13. Now in the multiplication rule, we talked about events that are independent or dependent. When we're looking at the addition rule, we talk about whether events are what is called mutually exclusive. And mutually exclusive is when events cannot occur together. Events that cannot occur together. So, this then states what occurs in the formula when the events are mutually exclusive. Well, we determined up here that when we roll a die, we cannot get a 3 and a 6 at the same time. These two numbers cannot occur in one roll together. So this would be considered mutually exclusive. All right, here, the king and the 3. There's not a card in the deck of cards that has a king and a 3 that happens at the same time. So these two events cannot occur together. So they are mutually exclusive. Now, in this last example, well, we know there's a card that is a king and a heart at the same time. So these two events can occur together. So these two events are not mutually exclusive. All right, so then it asks, what occurs in the formula when they are mutually exclusive? Well, both times that they were mutually exclusive, this last part of the formula was always 0. And that's what will occur. All right, so let's apply some of that information, but in problems like this. Now, when you're dealing with probabilities, and we're getting ready to read through this, and in the problem, they give us probability definitions. So you need to always be sure that you take the time to write down and define the probabilities that are given. That will make your life a whole lot easier. Professor Gill is in charge of a program to prepare people for a high school equivalency exam. Records show that 85% of the students need work in math, 65% need work in English, and 55% need work in both. So each one of these is a probability written as a percentage. So we need to define these probabilities. All right, so it says, records show that 85% of the students need work in math. So the probability that they need work in math, and I'm just going to do that a capital M, is 85% of the time, or 0.85. 65% need work in English. So the probability that the student needs work in English is 0.65. And then this last one says 55% need work in both. Well, what is in both? Well, that is math and English. So the probability that the student needs work in math and English is 0.55. Now previously, when we had an and, we were we did also apply the multiplication rule, but we don't have to do that here because they gave us that probability. There's not any work involved in it. Okay, the first question. Are the events needs math and needs English mutually exclusive? Now remember that mutually exclusive means that they cannot occur together. Okay, so let's think through this. Are there any students that need both? And absolutely. So since it does occur that some need in both math and English, then no, these are not mutually exclusive. Why or why not? Because 55% need work in both. So since they can need work in both, they are not mutually exclusive. So it says compute the probability that a student selected at random needs math or English. Okay, we have this word or here. Okay, so we're looking for the probability math or English. So now I know what it's asking, so now I can apply my addition rule. So this would be the probability of math plus the probability of English minus the probability of math and English. So now what I'm going to do is I'm just going to substitute these probabilities that we defined. The probability of math was 0.85. The probability of English was 0.65. Now, a lot of times students will neglect or forget to do this part. Well, there's a problem with that. One, it's not correct. But what happens when I add 0.85 plus 0.65? They would tell me the probability then would be 1.5. Well, that should raise a red flag for you because we have talked about and defined that probability always, always, always has to be a number between 0 and 1, and 1.5 would be too big because we have some students that are a part of this 85% and a part of this 65%. So we have to subtract those that need help in both, which would be 0.55. So then I subtract the 0.55 and I get 0.95. So that is my probability. All right, now the next examples that we do, so the following examples will be applying one or both rules, meaning it might need the multiplication rule, it might need the addition rule, it might need both. So let's take a look at this example. Now this is going to be another one where we need to define the probabilities that they give us in the problem. Sam is applying for a bank loan to open a hamburger franchise. Sam must complete a written application and then be interviewed. So there's a written application and then he has to be interviewed. So it looks like those are our two things going on here. Past records for this bank show that the probability of being approved in the written part is 0.59. The probability of being approved by the interview committee is 0.80 given that they were approved on the written part. So as soon as you see this word given, you know that that probability is a conditional probability. So we're going to have to be careful on that one. And then it asks, what is the probability Sam will be approved on both the written and the interview? So I see the and, so I know I'm going to apply the multiplication rule. Okay, well first I need to define the probabilities given. So I'm going to look back up here to this first sentence where I see 0.59. Past records for this bank show that the probability of being approved on the written part is 0.59. So the probability of being approved on the written is 0.59. Now, this next sentence, this is why I highlighted this. This tells me I have a conditional. So it says the probability of being approved by the interview committee is this number. So be careful. You're not just going to do the probability of interview equals 0.80, because we have the probability of being approved on the interview given the candidate has been approved on the written, and that is 0.80. So now it asks me, what is the probability? So here's the question being asked. These two were defined in the problem. Now we're going to answer the question. What is the probability Sam will be approved both on the written and the interview? Well, since this is an and statement, I'm going to apply the multiplication rule, which would be the probability of written times the probability of interview given written. And of course that is approved. I'm just not putting in that word. I'm assuming that. So the probability of approved on the written we define to be 0.59 times the probability of approved on the interview given they were already approved on the written. We have defined that to be 0.80. So now all I have to do is multiply 0.59 times 0.80 and we get 0.472. All right, next example. We are going to roll 2 fair dice, a blue die and a green die. Okay, so we have 2 die. So I'm not going to make my die. I just want you to understand we have 2 different die. One of them is blue and one of them is green. So we know this die has 6 sides, 1, 2, 3, 4, 5, 6, and this die has 6 sides, 1, 2, 3, 4, 5, 6. Okay? All right, so it says what is the probability of getting an odd number on the blue die and a 2 on the green die? All right, so, and the probability of getting an odd number on the blue die times the probability of getting a 2 on the green die given or assuming we got an odd number on the blue. Now, there's only one event. We're picking up both die and rolling them at the same time. Well, no, I take that back. You can roll them separately. That's fine. Okay, so pick up the blue die. When you pick up this blue die and roll it, what is the probability that you get an odd number? Well, 1, 3, or 5. So there are 3 sides out of 6 sides that have an odd number. So now what we're going to do is pick up the green die. Now we're assuming we got an odd on the blue, but now when I pick up the green, it's independent from the blue die, so I just want to know what's the probability of getting a 2 on the green die. And there's one side that has a 2, 6 sides. So that would be 3 over 36, which reduces to 1/12. So then it's saying now, well, what's the probability I get a 2 on the blue and an odd on the green die? So now it's just switching. So it would be the probability of a 2 on the blue times the probability of odd on the green given we got a 2 on the blue. All right, so pick up this blue die right here. What's the probability you get a 2? Well, 1/6. Times, now pick up the green die. What is the probability that you get an odd number? Now we're assuming we got the 2 on the blue, so now on the green, what's the probability of an odd? Well, that's 3/6. So that would be 3 over 36, 1/12 reduces to. So they have the same probability. Now, let's look at the third part. The third part says the probability of an odd number on the blue die and a 2 on the green die. So this is the probability that we calculated here. So this one is 1/12. Here it says the probability of a 2 on the blue die and an odd number on the green die. So we already calculated this to 1/12. But it wants to know or. Well, or tells me to add these two. So I just add the two probabilities that we already calculated. 1/12 plus 1/12 equals 2/12, which reduces to 1/6. All right, we'll look at some more examples. Okay, so we are going to draw two cards with replacement. So you remember when it has with replacement, that tells me that they're independent events. All right, so the probability of a queen and a 5. All right, it's and. So we would have the probability of queen times the probability of 5 given queen. All right, so first draw, what's the probability you get a queen? 4 out of 52. Replace the card, so that makes it independent. And now what's the probability you get a 5? 4 out of 52. You multiply that and reduce it, and you get 1 over 169. That would be 16 over some big number, but I've already done the reducing for you. All right, now we have the probability of a 5 and a queen. So again, this is and, so it's the multiplication rule. So the probability of 5 times the probability of queen given 5. Well, on the first draw, the probability of 5, 4 out of 52. Replace the card. The second draw, what's the probability you get a queen? 4 out of 52. So that is the same probability, which reduces to 1 over 169. Now, this question right here, I see it every semester cause students problems, so be very careful of this. It reads, what is the probability of queen and 5 in either order? Now, I always get the answer, not always, but a lot of times, majority of the time, I get that answer to be 1 over 169 because they see queen and 5, 1 over 169, and they give me that as the probability. But because it says in either order, here's what that actually means. Because of the in either order, it means if you were betting on this in Vegas, you would win if you got a queen and a 5, or you would also win if you got a 5 first and then a queen. Because here's either order. Queen and 5, 5 and queen. So queen and 5 is 1 over 169. 5 and queen is 1 over 169. But because of the or, we add these two, so the correct answer is 2 over 169. So be careful on that when you see in either order. That sometimes throws students for a loop. All right, here we go. We've got another bag here. So we have a total of 12 marbles. I'm going to make my bag a little bigger. All right, so there are 3 red, 7 green, and 2 yellow. All right, we're going to draw 2 marbles. Okay, I need to take notice. Replace the first marble before drawing again. Okay, so again, this is independent because we are replacing here. So it wants to know what is the probability of getting a red and a green. So since this is and, the probability of red times the probability of green given that we got a red. All right, so my first draw. Look in this bag, what's the probability that I pull out a red one? 3 of them are red, 12 marbles. Put that marble back in the bag because it says to replace. Now what's the probability I'd get a green one? Well, there's 7 green and there's still 12 marbles. So that'd be 21 over 144. Woo, had a little brain skip there. Okay, that reduces to 7 over 48. All right, now the second it says repeat the example above, but now do not replace. So this would be an example of independent. This is an example of dependent. So we still want to know the probability of red and green. It's just that now we're not going to replace. So it's the probability of red times the probability of green given red. Well, on the first draw, when you reach in to pull out a red marble, there's still 3 of them, 12 in the bag. But now assume that you're holding a red marble in your hand. Now what's the probability of getting a green? Well, there are still 7 green marbles in there, but there were only 11 marbles left in the bag. So when you do that multiplication and then reduce, let's see, I'm going to do it on my calculator. I have it, but I want to make sure it's correct. So I have, which I know is 1/4. So I have 3 over 12 times 7 over 11. And I get 7 over 44, which makes sense because 3/12 is 1/4. So 1 times 7 is 7, 4 times 11 is 44. All right, so there is using sometimes the and, sometimes the or. Now this last example is reading from a table or a chart. So probability using contingency tables. All right, so here we are given the results of 2 approaches to selling a customer a vehicle. So what this tells me is that a customer was approached aggressively when they were buying a car, and another customer was approached passively. So we have a total of 580 that were approached aggressively, 580 that were approached passively. The total number of customers then would be 1,160. Now our columns is, of those 1,160 customers, 686 of them bought a car, 474 of them did not buy a car. Now these numbers we'll talk about here in a little bit. Okay. So, this says, what is the probability a customer was approached aggressively? So I look at aggressive and I go to the total. There were 580 of the 1,160 that were approached aggressively. And that simplifies, to 1/2, or you could put 0.5. What is the probability that a customer did not buy a car or no sale? So the total of that would be 474 of the 1,160 did not buy a car. And that simplifies to 237 over 580. Okay, now on this next one we have a conditional probability. And this is where you need to be careful on these conditional. Now remember, conditional means that there's a condition placed on it. So we are restricting our attention to the portion of the sample space satisfying the condition. So this says, what is the probability a customer was approached aggressively given they bought a car. So we're only interested in those customers that bought a car. We're not interested in all 1,160 of them. So the second part that is your condition is what you restrict what you look at. So we're not interested in all 1,160. We're only interested in those in which a sale was made. So the probability that they were approached aggressively given a sale aggressively would be 270 of the 686 of them that bought a car. And that reduces to 135 over 343. Okay, now, just so we can look at the table too, I'm going to fold this a little bit so we can look at the probability question and the table at the same time. So just hang with me for a second. Okay, so this next one is a conditional probability as well. And now the condition is saying only look at those customers in which they were approached passive. So what I'm going to do is restrict my attention to only those that were approached passively. So I'm not worried about those, nor am I worried about those. So the total that were approached passively, we're looking at only 580 customers. So that's going to be my denominator. So I know my denominator is going to be the 580 and no sale. So I'm restricting to this row of passive. No sale would be 164. And 164 over 580 reduces to 41 over 145. All right. Now we're going to look at aggressive and sale. Look here, and. So if we go back to our multiplication rule, that would be the probability of aggressive times the probability of sale given they were approached aggressively. Now if you'll look up the probability of aggressive, we calculated that in part A. So aggressive, it was, now it did reduce to 1/2. I'm going to leave it in not simplified form yet, and I'll show you why here in a little bit. So 580 over 1160. Get this back up. So 580 over 1160 times, now in part D we did no sale given passive. Let's see, we did aggressive given sale. So we have not done this one yet. All right, so here we have a conditional probability. I'm going to restrict it to given aggressive. So here's aggressive. It is a row. So my denominator is the 580. And sale would be the 270. And here's why I did not reduce that first fraction. That cancels that out. I get 270 over 1160, which reduces to 27 over 116. Okay, let me do this last one with you. Move this so we can see this. Now we have an OR. So this is my addition rule. So this would be the probability of aggressive plus the probability of sale minus the probability of aggressive and sale. All right, well this was done in part A. Probability of aggressive was 580 over 1160, and I'm going to leave it in unreduced form until my final answer, because I'm adding and subtracting and you have to have common denominators. So I'm going to make sure my denominators stay the same. All right, now what is the probability a sale is made? Well, here's sale. The total would be 686 over the 1160 minus the probability of aggressive and sale. Well, aggressive and sale is what we did in Part E, and that was 270 over 1160. Now, since this is not zero, that tells me that these events are not mutually exclusive. It means they can occur together. So we have common denominators, so I do 580 plus 686 minus 270. We get 996 over 1,160, and that reduces to 249 over 290. And that completes Chapter 2 notes.